Article 310.15 example 5 pertains to the derating of conductors within a wireway. This is a crucial aspect of electrical installations to prevent overheating and ensure safety. The primary focus is on the number of current-carrying conductors present in the wireway and how that affects the ampacity of the individual conductors. When a wireway contains more than 30 current-carrying conductors, the standard derating factors outlined in Table 310.15 of the National Electrical Code, or NEC, come into play. However, Example 5 provides an exception to this general rule. The exception outlined in Example 5 focuses on situations where the conductor ampacity has already been adjusted before entering the wireway. This is important because it means that the conductors have already had their ampacity reduced because of factors such as ambient temperature or the number of conductors in a cable or conduit. In such cases, you do not need to apply additional derating factors simply because the conductors are now located in a wireway with more than 30 current-carrying conductors. To properly understand this exception, it's important to fully define what a current-carrying conductor is. A current-carrying conductor is any conductor that carries electrical current under normal operating conditions. This generally includes phase conductors in alternating current, or AC, systems, and both positive and negative conductors in direct current, or DC, systems. Neutral conductors are also considered current-carrying conductors if they carry a significant amount of current. Typically, this means the neutral conductors in three-phase, four-wire systems where the majority of the load consists of nonlinear loads, such as electronic devices with switching power supplies. These nonlinear loads generate harmonic currents, particularly the third harmonic, which adds arithmetically in the neutral conductor. Grounding conductors, such as equipment grounding conductors, or X, and bonding jumpers, are generally not considered current-carrying conductors. These conductors only carry current under fault conditions, not during normal operation. However, if an EDC is intentionally designed to carry neutral current, it is considered a current-carrying conductor for derating purposes. Determining the number of current-carrying conductors within a wireway is a key step in establishing if derating is necessary. The total number of current-carrying conductors determines whether the basic rules of 310.15 apply. Remember, the exception in Example 5 only applies if the conductors have already been derated. Let's illustrate this with an example. Assume you have 40 current-carrying conductors in a wireway. Under normal circumstances, according to NEC Table 310.15, you would need to apply a derating factor based on the number of conductors. For example, if you have between 41 and 50 conductors, the derating factor is 50%. This means that the ampacity of each conductor would need to be reduced to 50% of its original value as listed in the ampacity tables such as those found in NEC Table 310.16. Now, let's say that these 40 conductors were initially part of a multi-conductor cable located in a hot environment. To account for the high ambient temperature, the conductors were already derated to 70% of their ampacity before being installed in the wireway. Because the conductors have already been derated due to ambient temperature, you would not need to apply an additional derating factor when they are placed in the wireway, even though there are more than 30 current-carrying conductors. In this case, Article 310.15 example 5 says that no further derating is required. However, it is imperative to maintain meticulous documentation of all derating calculations to prove that the conductors were appropriately sized and derated before installation in the wireway. It is also vital to ensure that the wireway itself is appropriately sized. The NEC specifies fill requirements for wireways to ensure adequate ventilation and prevent overheating. The cross-sectional area of all conductors within the wireway should not exceed 75% of the wireway's cross-sectional area. This requirement helps to ensure that there is sufficient space for heat to dissipate, even when the conductors are carrying substantial current. It's also important to understand the different types of wireways and their applications. Wireways are typically metal enclosures used to protect and route electrical conductors. They come in various sizes and configurations and are used in a wide range of applications, from industrial facilities to commercial buildings. Some common types of wireways include Firstly, NEMA 1 wireways, which are intended for indoor use to protect conductors from falling dirt, dust, and dripping non-corrosive liquids. Secondly, NEMA 3R wireways are suitable for both indoor and outdoor use, providing protection against rain, sleet, and snow, in addition to the hazards covered by NEMA 1. Thirdly, NEMA 12 wireways are designed for indoor use and provide protection against dust, dirt, dripping non-corrosive liquids, and splashing water. Fourthly, NEMA 4 and 4X wireways offer the highest level of protection, suitable for both indoor and outdoor use. These wireways are watertight and provide protection against corrosion. When selecting a wireway, you need to consider the environmental conditions in which it will be installed and the type of protection required. It's also important to select a wireway that is large enough to accommodate the conductors that will be installed within it while still adhering to the NEC fill requirements. Additionally, proper installation techniques are critical to ensure the safe and reliable operation of wireways. This includes properly supporting the wireway, making secure connections, and ensuring that all covers and access panels are properly installed. Wireways should be supported in accordance with NEC Article 376.30, which specifies the maximum spacing between supports. The spacing depends on the size and type of wireway, but generally should not exceed 5 feet for metal wireways and 3 feet for non-metallic wireways. Secure connections are also essential to prevent loose connections and potential electrical hazards. All connections should be made using appropriate connectors and fittings that are listed for use with the type of wireway being installed. When installing conductors in a wireway, it is important to avoid sharp bends and to maintain adequate spacing between conductors. This helps to prevent damage to the insulation and to ensure that heat can dissipate properly. Conductors should be neatly arranged and bundled together using cable ties or other suitable methods. It is also a good practice to label the conductors to facilitate future maintenance and troubleshooting. In summary, Article 310.15 Example 5 provides an exception to the general derating rules for wireways with more than 30 current carrying conductors. This exception applies when the conductors have already been derated for other factors such as ambient temperature or the number of conductors in a cable. To properly apply this exception, you need to carefully document all derating calculations and ensure that the wireway is properly sized and installed. Remember that safety should always be a top priority when working with electrical systems. Always follow the NEC and other applicable codes and standards, and consult with a qualified electrician if you have any questions or concerns. Adhering to these principles will help ensure the safe and reliable operation of your electrical system. Considering ampacity adjustment, you should be familiar with NEC Table 310.15 Bone, which provides ampacity correction factors for ambient temperatures other than 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature exceeds 30 degrees Celsius, the ampacity of the conductor must be reduced. If the ambient temperature is below 30 degrees Celsius, the ampacity may be increased. The correction factors are based on the insulation temperature rating of the conductor. For example, if a conductor has a temperature rating of 75 degrees Celsius and the ambient temperature is 40 degrees Celsius, the correction factor is 0.88. This means that the ampacity of the conductor must be reduced to 88% of its value as listed in Table 310.16. For more than 3 current carrying conductors in a raceway or cable, NEC Table 310.15 cone provides adjustment factors. This table reduces the allowable ampacity of conductors based on the total number of current carrying conductors in a raceway or cable. The adjustment factors range from 80% for 4-6 conductors to 45% for 21-30 conductors. When applying these adjustment factors, you should always round down to the nearest whole number. If the calculation results in a fraction of an amp, you should round down to the next lower amp. These factors are cumulative. If you have conductors exposed to high ambient temperatures and multiple conductors in a raceway, you must apply both the temperature correction factors and the conductor adjustment factors. This can significantly reduce the allowable ampacity of the conductors. The intent is to ensure that conductors do not exceed their insulation temperature rating under normal operating conditions. This prevents premature insulation failure and reduces the risk of electrical fires. It's also important to consider voltage drop when sizing conductors. Voltage drop is the decrease in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, you can increase the size of the conductors. Larger conductors have lower resistance, which reduces the amount of voltage drop. You can also reduce the length of the conductors by locating equipment closer to the power source. In some cases, it may be necessary to install a voltage regulator to maintain a constant voltage level. When working with electrical systems, it is important to use the proper tools and equipment. This includes insulated screwdrivers, pliers, and wire strippers. You should also use a multimeter to measure voltage, current, and resistance. Always de-energize circuits before working on them. Use a voltage tester to verify that the circuit is de-energized. Wear appropriate personal protective equipment, including safety glasses and gloves. If you are not comfortable working on electrical systems, you should hire a qualified electrician. Working with electricity can be dangerous, and it is important to take the necessary precautions to protect yourself and others. Consider continuous loads. A continuous load is a load that operates for 3 IOs or more. The NEC requires that conductors supplying continuous loads be rated for 125% of the continuous load plus 100% of the non-continuous load. This ensures that the conductors are not overloaded and that they can safely carry the current required by the load. For example, if you have a continuous load of 20 amps and a non-continuous load of 10 amps, the conductors must be rated for at least 35 amps. 20 amps x 1.25 plus 10 amps equals 35 amps. Additionally, you must protect conductors against overcurrent with fuses or circuit breakers. Overcurrent protection devices are designed to interrupt the flow of current if it exceeds the ampacity of the conductor. The NEC specifies the maximum overcurrent protection for different types of conductors. In general, the overcurrent protection should not exceed the ampacity of the conductor. However, there are some exceptions to this rule. For example, small conductors such as number 14 and number 12 American wire gauge, or OG, are permitted to be protected by 15 amp and 20 amp overcurrent devices, respectively, even though their ampacities are lower. It's important to choose the correct type of overcurrent protection device for the application. Fuses are generally used for protecting circuits with high fault currents. Circuit breakers are generally used for protecting circuits with lower fault currents. Ground fault circuit interrupters, or GFCIs, are required in certain locations, such as bathrooms and kitchens, to protect against electrical shock. Arc fault circuit interrupters, or RFCIs, are required in other locations, such as bedrooms, to protect against electrical fires. When selecting overcurrent protection devices, you must consider the interrupting rating of the device. The interrupting rating is the maximum fault current that the device can safely interrupt. The interrupting rating must be greater than the available fault current at the point of installation. If the interrupting rating is too low, the device may fail to interrupt the fault current, which could result in a fire or explosion. In conclusion, understanding conductor ampacity, derating factors, and overcurrent protection is essential for designing and installing safe and reliable electrical systems. Always follow the NEC and other applicable codes and standards, and consult with a qualified electrician if you have any questions or concerns.